I'm Jonah McLeod, and joining me is Simplex Micro founder and CTO, Dr. Thang Tran, best known as the architect of the RISC-V vector processor shipping in the Meta MPIA chip. In episode 3, the conversation was around correlation, making sure the performance model reflects RTL. Episode 4 turns to a different question: how designers can use a model to experiment with the architecture. Let me start by asking, what configuration does the performance model support? And why does that matter more here than in RTL?
Exploration and configurations, which you cannot easily explore in RTL. Every change means a resynthesis run that takes days. In the performance model, changing the L1, L2 cache size or the memory latency are parameters that you can modify in minutes for performance model simulation. Being an IP company, configuration is an important feature. We are starting with the cache size and the memory latencies and expanding to instruction issue width, raster, vector raster width, and RISC-V custom standard extensions. The configuration are applied to both the performance model and the RTL. The performance model is not a shortcut around silicon accurate results. It is a way to find the right configuration before you commit to one.
Why do these configurations matter to designers specifically?
It comes down to PPA, performance, power, and area. And with RISC-V, designer actually controls three, all three parameters instead of inherit a fixed trade-off. Cache size and issue width are determined by the workload, not by some average cases. With RISC-V, you can add and or remove instruction entirely. For example, if there's no floating point workload, then the floating point unit is gone. Not disabled, not gate up. It is physically absent from the die. That is the real millimeter square, the real watts back. It matters most where area and powers are the constraints, not set the performance. Edge AI portable devices, anywhere you can not just add a bigger heat sink. Is also why our torque per second per millimeter square and torque per second per watt numbers against something like an H100 look the way they do. We are not carrying silicon that is not needed by the workload. ARM does not give you that option.
What else matters to designers beyond the raw numbers?
Visibility into why the numbers are what they are. The performance model gives you a graphical cycle level view. You can see instruction type, misprediction, cache miss. As the workload actually runs, you can zoom into a 50 instruction pipeline graph, instruction by instruction, for any stalling in the pipeline execution. That is what tell the designer whether they need to optimize the instruction scheduling or to add custom instruction or to do prefetching or whether catching a particular stream of data is actually hurting them or not. By the way, the data stream that I'm talking about is about cache pollution. You not just getting a number, you're getting the reason for the number.
What comes after the performance model and RTL?
The FPGA, normally FPGA is just a hardware emulation, but we are building it out further. A real proof of concept, not just a checkbox. It needs things the performance model does not. Trace, debug, and MMIO, memory map IO. We patent the graphical output for FPGA, giving the designers a level of visibility into the live hardware behavior. That is not available with the standard emulation tools. The payoff is that FPGA is a low frequency silicon that you can actually put Linux on live in front of customer. And that is a different kind of proof than set a charge.
Does moving to FPGA mean the performance model work is done?
No, if anything, the performance model is the foundation for everything later. Simplex Micro's roadmap includes RISC-V matrix multiplication, multi-core, multi-thread, and automotive. We are evaluating our own matrix multiplication approach as well as looking at the RISC-V matrix multiplication workgroup suggestion. For the multi-core, we are looking at data center workload. For multi-thread, is the efficiency of area and power for edge AI devices. And for automotive, we are holding patents on ASIC implementation for both the CPU and VPU. FPGA is one more tool, not an exit ramp.
Next time, we'll begin a new chapter in the series. We'll see you next time on Conversations with the CTO.